In this example, we have a trisubstituted cyclohexane. We have an ethyl group up top, a methyl group, then over here we'll have a chlorine pointing back. And what we want to do is figure out what the most stable conformation of this cyclohexane is. Okay, so let's just start by drawing a chair. And do your best to keep your angles as neat and straight as possible. Then what I'm going to do is number my carbon atoms. Okay, so I'll number this methyl group as 1 and just number around the ring counterclockwise like I would if I were doing IUPAC numbering. From there, then you also need to pick a carbon 1 on the cyclohexane and number around your ring. So now what we'll do is we'll put our methyl group on carbon 1 in the chair conformation. Since it's pointing up or out towards you, we'll just make this the up substituent, and that's the methyl in the axial position. And if you want to draw it in, of course we have a hydrogen in the equatorial position. On carbon 2, we have an ethyl group. Now in this carbon we also have two substituents. We have our axial substituent as well as our equatorial substituent. Now this ethyl group is pointing in the same direction as the methyl, so it's going to be this up substituent or our equatorial substituent on carbon 2. So let's make that our ethyl, and then our axial substituent is the hydrogen. Then if we come over here to carbon 4, we have a chlorine pointing down, trans to the ethyl group. So if this ethyl is pointing up, our chlorine needs to be pointing down, so chlorine is axial, and we have an equatorial hydrogen. Now what we want to do is do a ring flip. Remember what happens during a ring flip. Here's our down carbons. Those will become up carbons. And then our up carbons, those will become down carbons. Okay, so let's go ahead and draw our other conformer of cyclohexane. Okay, and what we'll do from here, let's go ahead and look at what happens with our carbons. Our up carbons became our down carbons. And then our down carbons became our up carbons. Okay, just like before, we can number these. So carbon 1 that was an up carbon is now this down carbon, and we can number around the ring. Okay, so now all we need to do is draw in our substituents. But remember, the axial substituents become equatorial during the ring flip, and the equatorial substituents become axial during the ring flip. So on carbon 1, our axial methyl becomes an equatorial methyl, and then our equatorial hydrogen becomes an axial hydrogen. On carbon 2, our equatorial ethyl becomes an axial ethyl, and our axial hydrogen becomes an equatorial hydrogen. And finally, on carbon 4, our axial chlorine becomes an equatorial chlorine. Our equatorial hydrogen becomes an axial hydrogen. So now we want to analyze this for sort of a relative stability, and we're going to do that through thinking about our 1,3 diaxial interactions that are happening from axial substituents. So in this first conformation, we have an axial methyl and an axial chlorine. The ethyl is an axial, so it's not suffering from those axial 1,3 interactions. In the second conformation, we have an ethyl group in the axial position, but our methyl and chlorine are in the equatorial position. So comparing these two structures, it's going to be more energetically favorable to have 2 substituents in equatorial position and only 1 in axial versus 2 in axial and 1 in equatorial. So this conformation suffers from 2 sets of these 1,3 diaxial interactions. This conformation here only suffers from 1 set of axial 1,3 interactions. From that, we can say that this conformation is the more stable conformation. Okay, and just recall what those A13 interactions are. So here is our axial substituent. If we go 3 carbons away, we have an axial hydrogen, and those bump into one another. The same thing happens in this direction. This axial substituent bumps in to this hydrogen here.